So, Eric, Base Labs and talking about the topic of the software-defined car, I think is probably a good starting point just to understand where we've been in the past, sort of up until maybe 10 years ago. An electronic control unit, more commonly termed simply ECU, had a single function. So we might have a windscreen wiper ECU, a headlight ECU, and each of those ECUs had maybe one or two sensors, something like a rain sensor and an ambient light sensor. How is the electrical electronic architecture, also known as EE architecture, changing, and what's driving that change?
Yeah, yeah, that's a highly relevant question. So indeed, in the past, we only had those ECUs that had a single function. But I would say it's also important to understand that those sensors that you mentioned, like rain sensors, they had, let's say, very small amount of data only. So they had an individual signal, maybe giving an indication whether it's raining or not, or what's the amount of rain. That's all. So I think we have two major things that drive this change. This is on the one side, the huge amount of data that the new sensors are bringing, like the cameras. Imagine high resolution camera images. Imagine radar sensors that have lots of detections that they are providing, and lidar sensors, of course, they also provide lots of data points that need to be transferred over the wire. So that's a really technical challenge. The bandwidth, or the device is the bandwidth question in the car. But the second thing which drives that change is that those new sensors, they all perceive the environment of the car, and they want to understand which other traffic participants are out there, and that's really the new thing. And for that we need processing, and a lot of processing power and algorithms. And I would say those two things that drive that change, and also introduce things like new domain controllers, high performance computing, and all these things.
Now that's an interesting point you make there about this change to different architectures, and as you said, the sensors are very varied. They're different sizes. They have different amounts of data that they're delivering, and they're delivering it at different sampling rates. But I think one of the other things we're seeing as well is that a single sensor is actually going to be used by more than one ECU, and that's a change from the way these automotive systems have been built in the past. Is that right?
Yeah, definitely. And although we always talk about a single sensor like a radar, especially if that sensor is used by multiple ECUs, as you said, then typically we also see that those multiple ECUs have different requirements towards the sensor. So it might be that one ECU requires a specific data format from that sensor, and what a specific data level even, and another ECU may require another data format from the very same sensor, or even data at a different level. So this makes it really much more complex than in previous architectures, I would say.
And so, what are the challenges that arise because of that? Because we've got now maybe one sensor at the front of the car, like you said, a radar, but that now needs to provide that data to multiple ECUs within the vehicle because they're all using that information for different things.
Yeah, I mean, if we talk about these ECUs and those requirements, then we always have the question how much processing also happens on the sensor side.
Right.
And this also has influences to the bandwidth that is then required. There are driving functions that have, let's say, lower requirements to the amount of data that such a sensor is providing. So more pre-processing or processing can take place on the sensor, but which also increases the processing power that is required on sensor side. We have other driving functions or ECUs that tell or that want to have the data at a more lower level, for instance, which requires less pre-processing on the sensor side, but more pre-processing on such a, let's say, central processing unit, for instance. And those things, they have to be combined, and they have to be present at the same system, the same car. So I would say that's one of the challenges that we definitely see, deciding on which level those sensors provide their data, how much pre-processing occurs on which side. And it's always, that's kind of a wave it's also kind of going through the industry with time, kind of. So we see that this also changes. And in one year, let's say, a lot of pre-processing takes place in the sensor side. And another year, OEMs and maybe even suppliers want to have more processing in the central ECU side. So it's really kind of a wave in the industry.
So the data from these sensors is being brought together, and it's a term. The process is normally termed fusing, so data fusion, and that sort of brings it into a sort of homogeneous form that can be used by the ECU. How is that implemented?
Yeah, that's a tough one. So actually, if we talk about fusing or sensor fusion, which is also a commonly used term there, then I would say it's rather an umbrella term for a bunch of algorithms and techniques that are out there that are already existent or present since years or even decades, but also algorithms that are currently heavily under development. So and there are different reasons for doing or because or why we are doing sensor fusion. One typical reason is that you want to reduce things like sensor noise. So think of a radar, for instance, that provides a distance measurement and an angle measurement of an object that is in front of the car. Then typically the radar provides highly accurate distance measurements, but it's not that good in observing the angle or the lateral position of an object. So now you can add a second sensor with opposite properties like a camera, which is good in observing the angle or lateral position, but it's not that good in measuring or observing the distance of an object. So if you combine those sensors, then in theory you get best of both worlds, and that's what sensor fusion is doing. That's one reason why we do this, combining the strengths of two sensors in terms of measurement noise and sensor errors. But another very important aspect or reason why we're doing sensor fusion is that you want to increase availability. So it might be that one sensor detects an object, but the other one does not. And by combining those two sensors, you can increase the availability of the system. And the last and the third very important reason is reducing false alarms. It's very often not very likely that the sensor reports an object, but actually there's no object at all there. And the other one can, let's say, reduce this false alarm rate. That's the third reason. And depending which of those things you are addressing in your system, the resulting algorithm can differ. But at the end, all of those algorithms, they typically address all of these aspects at once with, let's say, different weights of these aspects.
Yeah. So where's the sensor fusion actually deployed? Can it be deployed in the sensors, or is it typically deployed then in the ECU, or maybe do we have several sensors connected to an electrical system, to like a sub ECU that then fuses the data together and then parses it in a common format to a domain controller or an HPC?
All of the options are valid and all of the options are done at the moment in the industry. So we see sensors that do sensor fusion inside the sensor. For instance, there are camera sensors where you can directly connect a radar, an additional radar sensor to the camera sensor. And then the camera is kind of the master, also the master processing unit. Also, the opposite or vice versa is also possible. You have the radar as the master and get some data from the camera. That's an option. But last time, more and more, also OEMs want to do this centrally. So sensors just provide their data at certain levels, and then the sensor fusion is taking place on a central processing unit. This is also because the lower the data level gets, the more processing power you need. And then, at least for modern system and higher automation systems, you really need much more processing power in terms of CPU or even GPUs, depending on the system that you have in mind.
Now, obviously we're seeing a lot of new sensors in the vehicle compared to a decade ago. There's short range and long range sensors. You've mentioned cameras already as well, and all these are being used for advanced safety systems, and even there's a looking towards implementing autonomous driving. Those sensors, what sort of information do those sensors deliver? How much is the information already processed by the time it comes into the sensor fusion software block?
Yeah. Although there we see a wide range of options in the industry, and I wouldn't say there is a standard yet established. For instance, look at the camera sensor. There we have what is typically called smart sensors that provide a list of objects. For instance, where each of those objects in the list consists of position, velocity, driving direction, acceleration, length, width, those properties on an object level. That's a very typical approach that we also see for the ADAS that we have in the market today. But staying on the camera side, newer system, they cannot really work with that level of data on the object lists. They, for instance, require to get the images directly with some semantic label attached to each of those pixels. And you can imagine that this increases the amount of data a lot, but also increases the information that it's still in the data. And the more you go to higher levels of automation, the more data or the more information about the environment you need. And this drives this data level going towards lower levels. Yeah, it's a similar thing for radars. In the past, we saw a lot of smart radars. Again, they provided a list of objects, each of those objects with position, driving direction, velocity, and so on. Newer systems, they go one level below that, where you get detections. So which also means that for a single object, you may get multiple points along the car, for instance, on the road. And this is then called high resolution radar, where we get hundreds of those points. And if you go to LiDAR, then you get thousands or tens of thousands or even hundred thousands of points of the vehicles surrounding per shot per cycle, which means if you have a sensor at 20 milliseconds update rate, then you get this 50 times a second. So a lot of data is coming and need to be processed.
And so when the data's coming in, how is the Base Lab solution presenting that data to the systems that are in the vehicle so that they can make an intelligent decision? Because obviously this is a safety critical functionality in many cases for guiding the vehicle, getting it in lane, or maybe making a decision as to whether to brake promptly because there's a pending accident about to happen.
Yeah, that definitely. Again, this depends on the driving function, and there are different levels for that output as well. So if you look at today's ADAS functionalities, then typically customers request us to provide lists of objects again. So then in the simplest case, lots of lists go in to such an algorithm from Base Labs, and again, a list of object gets out, but with better properties, higher accuracy, less false alarms, and maybe an even higher detection rate or availability. So all the things that come with sensor fusion, they also come at that level. There are other customers and then driving functions that need the output of such a sensor fusion at a lower level. For instance, there we provide an output on what we call a cell level, right, where you have the world discretized in a bunch of cells, tens or hundred thousands of such cells, and where each cell represents whether this region is occupied by an object or not. And if it's occupied by an object, what's the speed or the velocity of that object, and what's the driving direction, once again. But it's at a lower level where the base of software, for instance, didn't decide which of those cells build an object or not. This then comes at a later stage on the customer side. And there are driving functions that never require that an object representation has been built. They always operate on such lower levels.
So obviously a big part of this move towards software-defined vehicles is that now we're making software responsible for our safety, and I mean that's something that the aerospace industry has been tackling for decades already. But obviously there's a significantly smaller number of aircraft flying around in comparison to the number of vehicles on the road under completely different conditions. So how does a company like Base Labs ensure the quality of software, which is essentially a framework? You don't know as you're developing this framework how it's going to be used and necessarily which sensors are going to be attached in every possible use case, and therefore to ensure the safety of the software that's being put into these systems.
Yeah. That's a highly relevant question. So at the end, for at least some of the aspects, we do it very similarly to the other industry that are in the market since decades. So following standards development and processing processes or standards according or that relate to the processes how you develop the software. In automotive industry, the most common standard is the ISO 26262 for functional safety. That's something that we follow. Our software is also certified according to that standard, up to a safety level or rating of ASIL B. So you probably know there are 4 of these ratings from A to D, and B is the one we got certified for our software. So we follow those standards. Also things like ASPICE development processes, which are well established processes. And then, of course, we are doing tests a lot. And I mean, this is a topic by itself. And of
Yeah,
course, we are doing the things that have to be done, testing with simulated data, so artificial data, but also testing with customer data. So in fact, most of the data that we have and that we use for testing is coming from our customers, from real vehicles with real sensor setups. Because at the end, the edge cases that they are hard to find using simulated data only. At the
exactly.
end, you
Yeah.
need the data from the real scenarios, from the real world. And our approach is taking the data from the customers, putting them into the software, and then testing whether it's doing the right things.